Okay, so up to now, we have been mainly trying to come up with a description of nature that is consistent with, let's say, our sample case was the Stern-Gerlach experiment. So that was what our aim was. And at the end of the day, the description we have is that the state of the system is described by the ket space, which we define, let's say, which we showed in this form. And in this ket space, we can choose some basis, and most of the time it will be more convenient for us to choose a basis in which some observable is diagonalized. Let's say A is our observable, alpha is, let's call it alpha I. If it's an eigenstate, eigenket, then it satisfies such an equation. And well, in fact, a consequence of this was that we had this commutation relation, the momentum and the position, but it's just basically a consequence of the fact that we are describing our system using kets. It immediately follows that the momentum operator and the position operator, they do not commute. And hence, we have this famous momentum coordinate uncertainty relation. This should be larger than or equal to h bar squared over 4. So basically, our way of describing it led us to this uncertainty relation. In classical physics, we are describing nature in a different way. We are describing nature in terms of the position of the particles and the momentum of the particles. And in this description, there is no such uncertainty. Because there are no operators, basically. We don't need to deal with operators. Since we are not dealing with operators, we don't need to worry about the commutation relations, etc. So there is nothing left. So for example, it was Einstein's dream that maybe we can come up with an alternative description of nature, which is able to explain the quantum phenomena like the Stern-Gerlach experiment, the interference, etc. But at the same time, it doesn't give us such an uncertainty relation that it would allow us to determine the position and momentum of a given system at the same time. But up to now, we don't have such a description. And in fact, experiments seem to confirm the fact that certain observables are incompatible with each other. There's no way to determine both of them at the same time. And it just turns out that momentum and coordinate is just a pair of such observables. Now, up to this week, we have been always dealing with mainly a description. So we didn't really discuss how the observables evolve in time. Basically, we didn't describe, we don't yet have an analog of Newton's second law, let's say. Newton's second law basically describes us how the time evolution of a system is. At the moment, we don't have this analog. So this week, we will start looking at the dynamics, how the systems evolve in time. Now, do you have any questions before we start with the dynamics? Okay, so again, we will have our states. We will describe them as kets. Let's say we have some ket alpha at the time t0. So we just create our state at the time t0 to be in the ket alpha. And then, of course, the system will evolve in time. So that is what we would like to describe now. So the ket of the system will be some other ket at the time t. So this is our ket at the time t, given that at the time t is equal to t0, it is given by the ket alpha. So basically, alpha t0 at t is equal to t0 is our ket alpha. Now we will assume, well, this is just another ket in our Hilbert space. And alpha t0, let's say at t is just some other ket, again in our Hilbert space. And in principle, we can just relate these two kets in our Hilbert space by an operator. Let's say U takes a ket at the time, so this is t0, at the time t0, and converts it into a ket at the time t. So we will assume that there exists such an operator. That given our ket, any ket at the time t0, it allows us to determine the ket at the time t. Okay, so there are several assumptions I already made here. One is, I am assuming that it exists. That's an assumption. I am assuming that it is independent of the ket alpha. So whatever the ket here is, I could just choose some other ket, it will be the same operator. Now, what should be some of its properties? Now, first of all, we would like to conserve this inner product. This should be equal to alpha t0, alpha t0. Well, this basically means that if you normalize your ket to be 1, its normalization should not change. It means, for example, if you start with one particle somewhere in space, then it's the integral of the wave function squared over all space. It was 1. The particle, if it stays all the time, so you will always have that particle, assuming it's a stable particle, like the electron. After a time t, the probability that you have a particle somewhere is still 1. So that is why we want this equality. Now, of course, in particle physics, for example, when you are studying unstable particles, you can describe such systems by releasing this assumption, let's say. Because you might start with a particle, but after some time you might not have that particle, so the probability need not be conserved in that case. But for this course at least, we will stick with this assumption. Now, what does this mean? So let's just look at the left-hand side. The left-hand side is just, let me just use this notation, U dagger, TT0, U TT0, alpha, because basically this is nothing but alpha T0T, and this is nothing but the ket. This should be equal to alpha alpha, whatever the value of alpha is, whatever the ket alpha is. But this basically tells me that this operator over here should be 1. The identity operator, or U is a unitary operator. So we should have this the time evolution should be described by a unitary operator. So that is one thing we would like to have. Now, another thing that we would like to have is, let's say we start with alpha T0. T0, this is at the time T0. We evolve it to some other time and it becomes T0, let's say T0 plus delta T1. We just evolve it by delta T1. And then we can just evolve this ket once more. Delta T2. So this is at the time T0 plus delta T1 plus delta T2. Well, this whole step is a single evolution. I can describe this whole evolution of my state by a single operator. So you see, here I have U of T0 plus delta T1, T0. Here I have U of, at this step I'm using T0 plus delta T1 plus delta T2. Well, let me write it somewhere else. T0 plus delta T1. So this operator evolves from T0 plus delta T1 to T0 plus delta T1 plus delta T2. But I should be able to write the same thing as a single step as an evolution from T0 to T0 plus delta T1 plus delta T2. So basically this evolution is U of T0 plus delta T1 plus delta T2 from T0. So for me to be able to write this two-step as a single evolution, I should have this identity. U of T0 plus delta T1 plus delta T2, T0. This should be equal to, I evolve from T0 to T0 plus delta T1. Then I evolve from T0 plus delta T1 to T0 plus delta T1 plus delta T2. The left-hand side and the right-hand side, they should be equal to each other. So these are the two properties that I would like my time evolution operator to have. This one and also this one. Well, these are in fact similar to some of the properties that we had derived for the translation operator. So let me check the convention in your book. Let me look at a very small time evolution first. Let me check U of T0 plus dt. So and also one more thing, one more property that I know before we start studying its properties. Alpha T0, this is equal to alpha T0. Well, indicate is equal to itself. But I can just write this as I evolve this state from T0 up to T0. This identity should also hold. Well, this basically tells me that no evolution, no time evolution is the identity operator. This is the third property I have of this time evolution operator. Any questions up to this point? So basically what I want this time evolution to be unitary. I want the no time evolution should be the identity operation. Furthermore, if I evolve my state twice, one from T0 to T0 plus delta T1, then from T0 plus delta T1 to T0 plus delta T1 plus delta T2, I should be able to write this whole thing as a single time evolution from T0 to T0 to the final time. So those are the things I require from this time evolution operation. Now, since it is very close to 1 for no evolution, let me write U from some initial time T0, the evolution by dt in this form. Well, if dt is 1, if dt is 0, it should be 1. That is my boundary condition. That is automatically satisfied. Let me add the first order correction to this, minus I omega dt. Let's see if this satisfies our conditions, or under which conditions this satisfies our requirements. It automatically satisfies this one. If I set that dt to 0, then it is automatically 1. What else I want? I want U dagger T0 plus dt, T0 multiplied by U T0 plus dt, T0. This should be equal to 1. Well, let me write it out. This is 1 plus I omega dagger dt, 1 minus I omega dt. Of course, here, keep in mind that I have corrections of the order of dt squared, etc. This is not an exact equality. This is approximately valid when dt is very small. And I will always ignore the terms that are of the order of dt squared. So up to terms dt squared, if you just multiply this out, this is 1 minus I omega minus omega dagger dt plus terms of the order of dt squared. Well, you see, I'm anyway omitting any term that is of the order of dt squared. So up to terms of the order of dt, I should have 1 should be equal to 1 minus this expression. But that tells me that this expression should be 0, which tells me that this operator omega should be Hermitian. So here we have some other observable. Just like in the case of translation, we had this operator that generates translation had to be Hermitian. Now here we have an operator that generates translations in time, and that operator should also be Hermitian. Now, so 2 of these 3 properties, this is now satisfied, assuming omega is Hermitian. This is automatically satisfied when we assume that there is such an expansion. And then the only last thing to check is that identity at the top. So let's see if that is also satisfied. So that basically tells me that u of t0 plus delta t1 plus dt1 plus dt2 from t0, this should be equal to u of t0 plus dt1 plus dt2 from t0 plus dt1, and then from the time t0 to t0 plus dt1. Let us write them out explicitly. This is 1 minus I omega dt1 plus dt2. Is this equal to, now I'm checking if this is also satisfied, 1 minus omega t2 d minus I omega dt2 times 1 minus I omega dt1. The right-hand side is 1 minus I omega dt1 plus dt2 plus terms of the order of dt squared. Now, on the left-hand side, I also have terms of the order of dt squared, meaning either dt1 squared or dt2 squared or dt1, dt2. So you see, this identity is also automatically satisfied. So as long as omega is Hermitian, this operator that I wrote over here, valid for very small values of dt, it satisfies all the requirements of this time evolution operator. There is one catch that I didn't mention. Do you see any flaw in my argument over here? Anything that might not be so correct? So what is the unit of omega? The unit of omega is equal to the unit of frequency. Well, the unit of frequency is the unit of energy divided by h bar. So you see, omega has the unit of energy over h bar. Omega generates time translation. If you look in classical physics, in classical mechanics, the Hamiltonian generates time translation. Hamiltonian has units of energy. So we postulate that omega is h bar over epsilon. H over h bar, sorry. Hamiltonian is Hermitian. It satisfies my requirements. So this omega, then there is this question, of course. You see, when we were discussing momentum operator position translations, we said that, okay, we have this generator of translations, which doesn't really have the unit of momentum. So we said that, okay, generator of translations, that operator has can be identified with momentum over some constant. And here we say that, okay, this operator omega, which generates time translations, doesn't really have the unit of the Hamiltonian, which is the generator of time translation in classical physics. But if we just divide it by some constant, it has the correct dimension. So is this constant and the constant in our identification of the momentum, are they the same constants? So that is one question that we should address. Well, you see, up to this point, such identifications are nothing but postulates. They are assumptions. Eventually, we should find some means of testing our assumptions. So we should, and one of the tests that we should perform is that, you see, although we are going beyond classical physics, we know that at least in the Stern-Gerlach experiment, we couldn't really study it, explain it using the classical physics, concepts of classical physics. We are devising an alternative description of nature. But nevertheless, we know that in most cases, classical physics works. I mean, you just throw a stone, the classical physics just predicts its trajectory almost perfectly. There's no problem with classical physics as long as it is applicable. What quantum physics tells us that classical physics is not applicable at all cases. It is a good enough approximation under certain circumstances. So whatever description we have of nature, it should somehow include classical physics in itself. And for example, one thing we will be driving later on is the x by dt should be equal to p over m. We will see that we will have exactly the same expression in classical physics, in quantum physics, with x and p being operators. For these operators, we will be able to derive this equation, and we can derive this equation only if the h bar appearing over here and h bar in our identification of the momentum operator, they are the same constants. So kind of the requirement that the classical physics in some form should be included in our new description forces us to identify this coefficient over here with exactly the same coefficient we had to use when we were talking about the momentum operator. So that is h bar, the same h bar. Otherwise, we won't get this equation. But there might be another problem appearing over here which I didn't even mention. You see, this time evolution depends on two parameters. It depends on t0, it depends on dt. Here I didn't write any t0 dependence. So in principle, this omega over here can depend on time t0. So that is something we should keep in mind. Well, if that depends on t0, look at this identity. This is omega at the time t0 in our definition. This is omega at the time t0. Oh, sorry, here. But this is omega at the time t0 plus dt1. So that is something we should pay attention to. If this omega and this omega are different, then we cannot sum them up in this form. Or can we? You see, here I have a omega at the time t0 plus dt1, but I can Taylor expand that one also. So it will be omega at the time t0 plus corrections that are proportional to dt1. Well, it's already multiplied by dt2. So the difference of this omega and this omega from that omega, possible difference, is over here. So omega can still be time dependent, but nevertheless, this equation over here holds. There's no problem with that. Now, we will have a problem when we are talking about finite time evolution. You see here, we looked at an infinitesimal time evolution. You see, in this definition of U, we started by studying an infinitesimally small time evolution. But eventually we would like to have a finite time evolution, let's say starting from 1 second to 5 seconds. But 4 seconds is not infinitesimal. But nevertheless, using this property over here, a finite time evolution I can always write as many infinitesimal time evolutions, just like we did in the case of the translation in coordinate space. So I remember, if you remember there, when we wanted to have a finite translation, what we did was we just divided it into n parts, and at each step we just evolved it by a very small amount. So we can do the same thing over here. Well, there are a couple of things we have to pay attention to. Well, the easiest case will be h is independent of time. That will be omega is independent of time. So u of t plus delta t, starting from t0 plus delta t, let's say, starting from some initial time t0, this will be equal to, well, let me write a couple of terms at least, u of from t0 to t0 plus dt, from t0 plus dt to t0 plus 2 dt, from t0 plus delta t minus dt to t0 plus delta t. Let's say here we have n terms, and dt is nothing but delta t over n. So we are dividing this finite time evolution into n parts, and I'm just writing this a single time evolution as n separate time evolutions. So this will be equal to 1 minus I over h bar h dt (1 minus I over h bar h dt). You see, this is evolution by dt, and that is given by this operator over here. This is evolution by a time dt. It is given by exactly the same operator. So since h is independent of time, all of these operators are exactly the same. So this will be equal to, now let me write it in this form. Here I have n terms. I can take the limit as n goes to infinity. Because you see, each one of these terms have corrections that are proportional to dt squared. So if I take the limit as n goes to infinity, those terms proportional to dt squared will just go to 0. And this just becomes, if you just take the limit, this is limit as n goes to infinity of exponential of minus I over h bar h dt raised to the power n. This is exponential minus I over h bar h times delta t. Yeah, you see, n times dt was nothing but delta t. And since I already took the limit n goes to infinity, any possible corrections that were proportional to dt squared, they just cancel. Because dt squared times n just becomes delta t times dt, but dt goes to 0. So this is what happens if h is independent of time. Now the second case. H depends on time. So we can explicitly write the time dependence, but h of t prime is 0. So the Hamiltonian at different times, they might commute with each other. This will also be a simple case. Well, we will basically do the same thing that we did over there. The only difference being that we should keep in mind that this h now depends on time. So u of t0 plus delta t, t0 will be equal to 1 minus h, this t0 plus delta t minus dt multiplied by dt, 1 minus I over h at the time t0 multiplied by dt. Now let me just write one term in this expansion. Not all of them, but just one of them. This is 1 minus I over h bar sum over dt of h of t0 plus n times dt. N goes from 0 up to n minus 1. You see, I have 1 in all the terms, but just the h over here, that gives me ht0 dt. I have 1 in almost from all the parentheses, including this one, but I get the Hamiltonian from the second parenthesis, that gives me ht0 plus dt, then ht0 plus 2 dt, etc. So if I just collect the terms that are linear in dt, this is what I will get. Okay. So let us do this one. Well, let me just use one shorthand notation. I will use h of t0 plus n dt hn. Okay, so u of t0 plus dt t0 is basically 1 minus I over h bar h0 dt, 1 minus I over h bar h1 dt, 1 minus I over h bar h2 dt, 1 minus I over h bar h n minus 2 dt, 1 minus I over h bar h n minus 1 dt. Now, among these parentheses, there are terms that are proportional to dt to the 0. If I open up the parentheses, if I would like to get the term that doesn't depend on dt, from each one of the parentheses, I have to pick up the term that doesn't contain dt. So I just multiply the ones. So that gives me 1. Then I will write down the terms that are proportional to dt. Among this expansion, I will have terms up to dt to the power n. But let me just, this is dt to the power 0. If I want to calculate the term that is proportional to dt to the 1, I will take the dt term from one of the parentheses, and I will take the 1 from the other parentheses. Okay? So I will take this term and 1 from the rest, so that will just give me minus I over h bar h0 dt. I will take this term from this parenthesis and take the 1 from all the rest, minus I over h bar h1 dt. Well, I will take this term, minus I over h bar h2 dt. Then I take this term from this parenthesis and 1 from the rest. I'm just multiplying out all the terms in all the parentheses. Minus I over h bar h n minus 2 dt, minus I over h bar h n minus 1 dt. This is what I did. Plus, of course, terms of the order of dt squared. How many terms are there of the order of dt squared? Well, to calculate the terms that are dt squared, I should take two parentheses, take the term proportional to the Hamiltonian in those two parentheses, and in the rest I should take 1. Well, I have n of them. I should take two terms from n term. So n times n minus 1 over 2 terms, plus of the order of dt cubed, etc. So basically, well, I'm just concentrating at the first term. These whole, all of those, I can just write it in that form over here. Okay. Okay, I don't care. I mean, you see, all of these terms for different n's can be different, but that's already over there. Of course, plus there are additional terms over there. It's not just these terms plus terms of the order of dt squared, which I didn't write down. But this is equal to 1 minus I over h bar dt prime h at the time t prime starting from t0 up to t0 plus delta t. Plus, of course, additional terms. Of course, I need to go ahead and calculate these additional terms. But, I mean, just open up those parentheses. An easier way, in fact, to obtain the same result so we have this equality. Plus, of course, each one of these has corrections. Well, this is equal to exponential of minus I over h bar h n minus 1 dt, exponential of minus I over h bar h n minus 2 dt, exponential of minus I over h bar h0 dt. Plus, of course, there are corrections of the order of dt squared, each one of those terms. This is equal to exponential of minus I over h bar, sum over n 0 to infinity, h n minus 1, no, h t0 plus n dt times dt, plus terms that are dt squared, but there are n of them. Well, now I can take the limit n goes to infinity, dt goes to 0. Well, you see here, this is, let me write that, dt times dt. I'm multiplying 0 with infinitely many terms. This might be finite. It turns out to be finite, but dt goes to 0, so this is just 0. But here I have dt multiplying n terms. This is not infinity, just n minus 1. This is just finite. This is just an integral. So this is equal to exponential minus I over h bar integral from t0 up to t0 plus delta t dt prime h of t prime. And you see, well, there we had the one term explicitly, that is the same thing as this one, plus corrections, if we just consider an expansion over here. Now, my question, where did we use the commutation relation? I said that this is correct if the Hamiltonian at different times are commuting with each other. At which step did we use that fact?
In the top line.
Here? No. At that step, we didn't use it. Even if the Hamiltonian at different times are not commuting, this equality is correct. This is also correct. Even if the Hamiltonians at different times are not commuting. This is not correct if the operators are not commuting. You see, in general, if you have two operators, exponential of A times exponential of B, this is not equal to exponential of A plus B if the commutator of A and B is non-zero. This is not correct. That equality. But that is exactly what I used in this third step. I had the product of many exponentials. I said that, okay, I can write it as the exponential of the sum of the exponents. But that is only true if the operators are commuting. This is equal to this one only if A and B commute. So that's why it is true for numbers. Numbers are you can just think of numbers as commuting operators. They commute with everything. So at that step is where we use the fact that Hamiltonian is commuting at different steps. Well, then there is the problem of case 3. H of t prime is non-zero if t is different than t prime. Well, basically in that case, you are stuck with this expression over here. You cannot take this step. Well, there are some approximations that we will be studying, some other definitions that we will be using to simplify it. Well, basically in that case, the u t0 plus delta t, well, let me say t1 from t0, it will have this expansion minus I over h bar dt prime h of t prime from t0 up to t1 minus I over h bar dt1 dt2 dt prime dt double prime t double prime from t0 up to t prime and t prime from t0 up to t of h of t double prime h of t prime. Now this is plus minus I over h bar squared plus etc. So we have such an expansion of u. Now we will study this such expansions later on, so I just leave it over there. Any questions? Time-dependent Hamiltonian. For example, you put an electron in an external magnetic field that is changing with time. Well, for example, you can have a magnetic field that has a fixed direction but changing in time, its magnitude. In that case, the Hamiltonian at different times will commute itself. But you can have a Hamiltonian that has a magnetic field that is changing both in magnitude and direction. Well, magnitude is not really important, it's changing its direction. Since the spin in different directions do not commute, Hamiltonian at different times will not commute in general. So you see, up to now, I mean, even about this Hamiltonian, the only thing we know is just some general properties. It has to be Hermitian. That is one property we know. And, well, basically that's all we know. So how do we construct this Hamiltonian? What is the Hamiltonian? Now, if you consider the fundamental physics research, what we are basically doing in CERN, etc., is basically trying to find out what this Hamiltonian of nature is. Of course, we know that if there is a classical limit of the particles, we have to be able to reproduce the classical physics results. So we have a kind of, let's say, some principles, guiding principles, which allows us to write down what the Hamiltonian should be. But if there is no classical analog, then there is no fundamental principle that tells us what the Hamiltonian should be. So we are just trying. Whatever Hamiltonian comes to our mind, we just try it, try to calculate its predictions for observables. And then if they match with the observables, then we say, okay, great, that might be our Hamiltonian. If not, then we try a different Hamiltonian. Well, you see, we are doing a quite good job in that. I mean, we have currently what's called the standard model, and kind of the Hamiltonian corresponding to the standard model can explain everything we do in accelerators and in our everyday life. Basically, the things that it cannot explain is, for example, it cannot explain gravity. That is unfortunately something we cannot add it yet. But of course, if you start from the standard model Hamiltonian, in principle, you can explain all the experimental results that we had, not observational, but experimental, the controlled experiments. We can explain all of them. But for practical reasons, I mean, starting from the standard model Hamiltonian and trying to study the spectrum of the hydrogen atom is quite a complicated task. So what we do is somebody just simplifies the Hamiltonian of the standard model, tells us that, okay, our standard model Hamiltonian is complicated, but in the case of the hydrogen atom, you can use a simplified version of that Hamiltonian. We just put this 1 over R law. If you want to get corrections, well, go back to the standard model Hamiltonian. So it also tells us what the corrections should be. So we calculate the corrections also. We get even better results. So the reason why we are using different Hamiltonians in different systems is that the fundamental Hamiltonian is not easy to deal with. I mean, if you start with the standard model Hamiltonian to calculate the spectrum of the hydrogen atom, well, you will probably spend your life, let's say. But for example, in the case of the hydrogen atom, we don't really care what the quarks are doing inside the proton. To understand the hydrogen, we can just treat the proton as a point particle. In that approximation, our Hamiltonian simplifies, and we get the Hamiltonian of the hydrogen atom. Okay, let's give a 10-minute break and then we will continue.